Hello. In this lesson, we are going to talk about even functions and odd functions. First of all, let's recap, right? Recap the definition of function, which is our centerpiece of this course. And it will be still the centerpiece for your next courses in calculus or pre-calculus. A function is a rule, right? So we've been discussing many different rules. A function is a rule that assigns to each element x in the set of A exactly one element called f of x in the set of B. And we have understood that, one is a rule and the other one is for the rule to be a function, we have this very specific requirement, which is for each element, right? So when we tweak the definition to make it shorter, that this function, which is a rule that has to satisfy this condition spelled out in the definition. So for each element or each input, right? For each input in the domain, it has to have exactly one output in the range, So every rule has its domain and range, and we talk about, the vertical line test. And we also have done, those examples of functions. And then we talk about the one-to-one function definition, right? One-to-one function definition talks about that if we have a function, what makes it one-to-one? So we have this definition in addition to the function requirement, right? Whenever the inputs are different, their respective outputs are different as well. So this is the requirement for being one-to-one function. And then of course we have the horizontal line test. And we also talk about what makes it not one-to-one function, right? So the definition for not a one-to-one function is such that for some, right? So the opposite of whenever is for some different inputs and their outputs are the same. And we also then talk about that if a function is one-to-one, it has exactly one inverse. So make sure you see that -1 over here, right? So each one-to-one function has exactly one inverse. And we talk about these three important features about a one-to-one function and its inverse. The graph, right? The feature about their graph, they're symmetrical with respect to a certain line. And the composition satisfy that relationship, right? And what is more is that one is the range, the domain of one is the range of the other, vice versa. And in the last video, we talk about increasing function and decreasing function and we given definition. And we have discussed the details on on these examples, which one is increasing, which one is decreasing. In particular, right? You look at the definition for inverse function. We all have, domain in our mind and range in our mind. For increasing function and decreasing function discussion, and in their definition, it doesn't have to be in the entire domain, but we need to specify the specific interval at which the function is increasing or decreasing. So we have done some examples, right? Such as, that this function is neither in the domain, in the entire domain considered, it's neither increasing nor decreasing. But if we specify the specific interval, then it is decreasing here and increasing on the other interval, right? So we have multiple examples of such case, right? So without further ado, we're going to talk about even function or odd function. Even function, odd function. Okay, so let's start with the definition. Okay, so I'm going to move to the very top. Okay, what makes an even function and what makes an odd function? The definition of an even function, first of all, it addresses to the domain of the function. Okay, so we say even function. Okay, so here's the statement. F is even if, right? There's a requirement for a function to be even. If f of negative x is the same as f of x for all of the x in domain, for all of the x in the domain of f. What does that mean? What does that mean? Right? F of negative x. So when you look at this, right, we know a function is a rule, right? A function is a rule. So when we look at this rule, we understand, and there's a rule here. So what is f of a negative x? What is f of negative x? Well, the negative x, right? Since this is for domain, so you can see the negative x has to be from the domain, right? The negative x has to be from the domain of f. Okay, so if x is in the domain, its opposite is also in the domain. So basically, we're saying for any number we have in the domain, if x is in the domain, its opposite is also in the domain. For example, if 2 is in the domain, then -2 must be in the domain as well. If -3 is in the domain, the opposite of -3, which is a negative of -3, is +3, is also in the domain. So when we have f of negative x, what it means is that this function, I'm sorry, this rule, oh, what's going on here? Okay, there, that should make it, okay? So this rule would apply to negative x, okay? You see negative x is in the input position. And the function work on the input. So that's how we produce this. We produce f of negative x. And this must be in the range of f as well. So this must be in the range as well. Okay, so you can see f of x, that's the flow. Negative x, the input, that's the flow. So what this definition says is for any x, okay? And it's opposite also in the domain. And these two quantities, okay, these two quantities, we don't need that. These two quantities are identical. They're always the same. Then it's an even function. It's an even function. Okay, so let's look at some examples as what it means. What's the means by on the picture, right? I'm gonna go to that big table, right? We have worked out so many examples here, right? We'll pick up one of those. And we have another table. Wait. My computer seemed to be rather labeled. Okay, so let's make it smaller. So this guy. Okay, so I'm basically bringing all of these functions together, which we have covered and we have gone over, and we're going to pick an example. I'm going to pick the example of f of x equals to absolute value of x. So this is the example I'm going to cover. Okay, the first example. We're going to examine, is it even, right? What it means on graph. So this is the graph. This is the graph. Now I make it larger so you can see. Domain, all real numbers, right? Domain is all real numbers. So this consideration has to be on the entire domain, has to be on the entire domain. Negative infinity to positive infinity. Okay, so is it true? Is it true, right? So this has to be true to make it an even function. So is it true? Is it true? So I put a question mark here, put a question mark for that criteria. Then we look at this function. We look at this picture, right? What it means, right? What is negative x, f of, what is x, what is negative x? Suppose I choose x, right? Suppose this is my x. This is my x. Okay? This is my x. What is the opposite of it? What is the opposite of x? So if this is x, right here, and what is the opposite of x, right? The opposite of it will be on the other side, right? Okay. So negative x, something like that. Okay. Negative x. This is x, this is a negative x. They're of the same length, different value. Apparently x is itself is negative and negative x is positive, right? Because they're opposite to each other. If this is negative, then it's positive. Its opposite is positive. Now, what are the output? This is the output. This is the output. Oh, okay. So this is the output for negative x. And this other one is the output for f of negative x. So this red piece, right? Because the input is x. So this red piece on this side is f of x. How about the other one? Because this piece is negative x, right? So this piece is f of negative x. I hope that's clear, right? Input, okay? Input, output. Input, output. And for this particular function, apparently these two are the same, right? Because they're taking absolute value of x or negative x, right? And it is true for any x. For any x, x can be 2, -3, 5, 2.6, -7/8, any number you name it from the domain. Okay, so now we can say, because, right, f of x equals to absolute value of x, right? F of negative x by the rule of the function is going to be the absolute value of negative x. the absolute value of x is the same as absolute value of x, right? The absolute value of negative x is the absolute value of x, they're always the same. Thus, f of x is equal to f of negative x. And this is true for any x in the domain of this particular function. And then you can say, thus, this function is even. That's it. That's it. That's it. Okay, you can see the even function has some very interesting feature. It's symmetrical with respect to the y-axis. It's symmetrical with the y-axis. Okay, so now we see the feature, we understand the geometric appearance and the features, right? So now let's take a second look. Let's take a second look of all of these functions we have discussed. Which one of these look like an even function to you? Which one of these it looks like an even function to you? Can you demonstrate it? Can you demonstrate by the definition to confirm your conclusion? Well, this function, the constant function, is even. Yes, it's even. It's symmetrical, right? It's always the same. As f of negative x is going to be constant, f of x is going to be constant for any number on the in the domain. So this is going to be a one-to-one. This is even function. How about this one? This one is not. This one is not. Why this one is not? Right? Why this one is not? Well, you can go by definition, right? Negative, well, if this is x, right? And that's negative x, the opposite input, right? And their output are not the same. So one is above, the other one is below. They're not the same, right? They're not the same. Therefore, this one is not. This one is not even, not even. Okay, so continue the observation. Continue the observation. Even, right? Even, because this function is even because of what? Because negative x squared and x squared are always the same. Negative x in parentheses squared, okay? This is what I meant. Okay, for f of x, right? For f of x equals x squared, it's even from the picture, right? And from algebraic, from definition, and you can tell that negative x squared is always the same as x squared, right? For any real number x, for any x in the domain of all real numbers. So negative infinity to positive infinity, right? Then you can say, because this is merely saying what? This is merely saying what? That is, for this function f of negative x is always the same as f of x, right? Feel free to use these notations and learn how to use these notations to make your point. Okay, and therefore you can say therefore, and this function is even. And we see that obviously from the picture, obviously from that picture, right? So this function is even. And go back, we talk about this function is even. How about this one? Well, this one cannot be even. Why? Because even function requires, if x is defined, the opposite of x is defined. And our domain is only for non-negative number. The opposite of non-negative number are, negative numbers. The opposite of positive number, negative numbers. And negative numbers are not in the domain. So this one cannot be even. How about this one? Not even, right? So that's the even function definition. So we also know the feature on the graph, right? So next definition we're going to go over is odd function. Okay, the odd function. Odd function. Okay, so I'm going to just change a few words. You see what I change, right? Okay, odd function. So f is odd if, okay, I'm going to put a negative sign here. Okay, that's all I need to change. That's all I need to change. But what is the geometric meaning of it? What is the geometric meaning of it? Okay, so now I'm going to approach this explanation in a slightly different way. Okay, what it means of negative x. What it means is negative f of x. The negative sign inside or outside, what difference it makes. Okay, so first we're going to address the difference between f of a negative x and, excuse me, and negative of f of x. What's the difference? They each have a negative sign. Okay, from the flow, what does it mean? The flow I talk about here, right? The flow I talk about here. Okay, x, negative x. So when we talk about f of negative x, this is what we meant. F of x. So when we put a negative sign in front of the x, what does that mean? You have to go one more step to negate f of x. The output, the opposite of the output. So you multiply by negative number, by -1, and then f of x. You guys see that? Okay, you see this negative sign. Okay, so for this one, that's the flow. For this other one, and that's the flow. You guys see that? That's the difference from the definitional function perspective, right? So what this does is that you take your x from the domain, and then you put a negative sign in front of it, and then you give this negative x as an input. And then you produce an output. Okay, so f of negative x means the input is negative x, and the output is f of negative x. Okay, input, output. And this other one, however, you start with x. And this x is the input for f. So we produces f of x. So this is already the output. And then we take the opposite of the output. So negative of f of x really meant is the opposite of the output. So this means the opposite of input the opposite of the input, and this is the opposite of output. That's the difference, right? All right, so now, next, according to this condition, okay, according to this condition, okay, the odd function condition, right? F is odd, then this condition must satisfy. So we had the explanation of the flow. So I'm going to explain this picture, okay? So what kind of picture we're getting if all of these conditions are set, if this condition is satisfied? Okay, so be very patient with me because I want to explain this to you so you have a good understanding of it. Okay, so this is the picture. Okay, this is a rectangular system. So I'm just going to make some adjustment so that it works properly. Okay, it shows the number properly. That's all I wanted. Okay, so what it means by that, right? So I'm going to put this picture right next to it, right? X, well, X as input, negative X, right? So now, suppose we have f of X. So first let's set up the X, okay? Suppose I have the X is this much. Okay, so this is my X. Input. I think I want to have a different color. Okay, I want to have a different color. Let's see, will that make it? So this is X. It doesn't change for me. So never mind. Okay, let's just keep it that way. Negative X as input. Okay, negative X as input. Negative X as input. So if this is X, if this long is X, right? Negative X is going to be on the other side. Okay, so I'm going to put this as negative X. Okay, and the curve, so we have an f of X, right? F of X. So for f of X, it's going to be what? Suppose f of X is this much. Okay, this is X and this is f of X. Give me red, please. Okay, so red. Suppose this is f of X. It's a little bit off, right? So let me make sure it is properly. So it's on the dot. It's on the dot. This is f of X. Clean this up. F of X, right? So I'm going to mark it as f of X. Okay, that's f of X. The output are vertical, right? Horizontal is input. Now, so input for X, output, input and the output for X. And what will be the input for the other side? It's negative X. So the output, right? F of negative X is opposite of f of X because you see there's a negative sign in front of it. So f of a negative X has to be what? Has to be over here. Has to be over here. Right? And then when we put a negative sign in front of it, we put a negative sign for f of X. So this, let me write it down. So that's the situation. So this is going to be f of negative x. Okay, this is f of negative x. If this is f of x, this is f of negative x, what is the negative of f of x? The negative of f of x is going to be flip over because that's the opposite of it. So this guy is negative. Okay, negative f of x. I hope that's clear to you. Otherwise, ask me questions, okay? So if these two are equal, when these two are equal, right? What kind of picture are we getting? What kind of picture are we getting? If these two, of course, f of x is a curve, right? So you have a piece on this side and you have a piece on the other side. If this doesn't help you to understand, so let's look at an example. Okay. This example I'm going to choose is going to be it's going to be one that's used used for sure in calculus class. Okay, x raised to the power 3. We know this curve, don't we? We know this curve, don't we? If we don't remember, well, I can just draw it on the spot, right? But just to, bring back the context. So this is f of x raised to the power 3. Very useful function used in calculus classes, right? Let me make some adjustment, just a little bit adjustment. Let's see. 2. Okay, so that makes it easier to see. So now, what is f of x, right? So basically we need to observe, right? We need to observe. We need to observe f of x and f of negative x to see if they are opposite to each other. Okay. All right. So suppose we pick an x. Make it green. And this is x. And what's negative x? Okay, so let me mark it. So this is x. And negative x is going to be on the other side. Okay, same length. Okay, all measured from the same spot, horizontal. So now this is a negative x. So when we power these two, by 3 power of 3, right? So let's look at the output. The output they're red. So this, oops, give me red, please. Yes. So give me red. So this is f of x. Okay. F of x, which equals to x raised to the power 3. Right? And the other red. And this is going to be what? This is going to be f of negative x, which is negative x raised to the power 3. Right? Now, what is negative of f of x? Negative of f of x, put a negative sign in front of it. So if I put a negative sign in front of f of x, what do I get? I'm getting this piece, the opposite of it, it will flip right over, right? All right, so this piece is going to be negative f of x, which is, if we plug in here, we put a negative sign here, this is going to be a negative sign there. On the other side, x raised to the power 3. You can see these two are the same, right? This quantity, negative x raised to the power 3 and the negative x to the power 3, they're the same quantity. They're the same quantity, okay? So what do we see here? Okay, so let me write it down here. This quantity, which is negative x raised to the power 3, is the same as negative x raised to the power 3. They're the same. Okay? This is an odd function. This is an odd function because these two, f of negative x and f of x, they are opposite to each other. They're opposite to each other. Okay? So now let me explain from the algebraic perspective. Let me explain from the algebraic perspective. We just explained from the picture and algebraic, right? So algebraically, algebraically, okay, algebraically, okay, the function is x raised to the power 3, right? By definition, right, this is the definition. By definition, right, odd function definition, we are going to check if these two are the same. Okay, so we're going to check f of a negative x. By the rule of the function, it's going to be just negative x raised to the power 3. Right? So we end up with negative x time itself 3 times, and we get a negative x raised to the power 3. Right? And the other aspect is, what is negative of f of x? Negative of f of x, you put a negative sign in front of it. F of x will be handled first, and which is going to be x raised to the power 3. And negative x to the power 3, negative x to the power 3, the same. So we ended up with what? This requirement. And this is going to be true for any x, because we didn't have to choose x with any specific value. These operations is true for any number in the domain of f. Okay, so f is odd. So this function, f of x, is odd. So the odd function in summary, what does it tell us? Odd function in summary, what does it tell us? When the input are opposite, the output are opposite as well. This is an odd function, right? So let's look at it again. When input are opposite inputs opposite inputs. You see the two inputs are opposite. Their respective outputs are opposite as well, right? Inputs are opposite, outputs are opposite as well, okay? So whenever, okay, whenever the inputs are opposite, their respective outputs are opposite too. Then it is an odd function. It is an odd function. Okay, so this is the feature of odd function. Okay, so odd function has such a feature. Now let's summarize. Even function is symmetrical with respect to y-axis in the entire domain. Odd function symmetrical actually with respect to origin. And whenever the inputs are opposite, the outputs are opposites. That's the feature for odd function. For even function, okay, for even function, let's see if we can make some narrative to help us understand, right? Even function, however, right? We know that even function, this is even function, this is even function. Whenever the inputs are opposite, the outputs are the same. The respective outputs are the same. So let's have these narratives written down. Okay. So let's have these narratives written down. So even function, odd function, right? Even function, odd function. So let's make a table to summarize their features, right? Even function, right? They're all on domain. Odd function, okay? And we call them F, right? The definition for even function is F of negative X is the same as F of X. For what? For all X in domain. Odd function, okay? F of negative X is equals to negative of F of X for all X in domain, for all the X in domain, okay? The feature on graph, the graphical feature, okay? The graph is that whenever opposite inputs, respective outputs are the same, okay? It's a little bit crowded, huh? But that's okay. We're just going to put it over here underneath, right? Just get rid of it, okay? So how about the next one? Whenever opposite inputs, respective outputs are what? respective outputs are what? Not the same, right? Not the same. Respective outputs are opposite. Opposite. Okay, so that's the feature we can describe. We can speak it. And you may just as well summarize some situations that's, you know, that's fitting for you. That's fitting for you. Now, are there functions that's neither even nor odd? Okay, are there functions, okay, that are neither even nor odd? Of course, right? For example, if we look back to the tables of function we have studied, right? Which one do you think is neither? It looks like this one is odd, right? This one is odd. Even. Odd, even. How about this one? This one is neither. This one is neither. It's neither even nor odd. Okay, so this one is pretty straightforward because you simply cannot do the opposite input. If you choose an input from the domain, the opposite of this input is going to be outside, except 0. Right? If you choose 2 from the domain, -2 is outside the domain. So you cannot even operate this function. Therefore, this function is neither, okay? Neither odd nor even, okay? So let me give you another example to show you the general procedures to demonstrate whether it's even or odd, okay? So example, right? So I have a function here, f of x, and this is going to be x squared plus x. Okay, so our question is this even, odd, or neither? Well, you can look at the graph. You can look at the graph, but I would also just look at the algebraic, okay? Because you can see in the sense of the definition, we mainly just compare f of x with f of negative x, really, right? So we already have f of x. So let's see what is f of negative x. So f of negative x is going to be negative x squared plus negative x. Right? Negative x squared is going to be equals to x squared because negative x times negative x plus negative x is going to be minus x. So right away, you can tell it's not even. Not even. Why? Because f of x is not the same as f of negative x. So we rule out the possibility of being even. Is it odd? Is it odd? To compare whether it's odd, you have to say, okay, if I put a negative sign, right? If I put a negative sign in front of f of x. So this is f of x. What is the negative of f of x? Right? You have to put a negative sign on this side, right? So the negative of f of x is going to be on this side. And what do we get? We get negative x squared minus x. So you would compare these two, right? Because that's in the definition. F of negative x, which is this guy, and negative f of x, which is this guy. So you compare these two. So we compare, by definition, these two quantities, these two. Are they the same? No, so not odd. Okay, because f of negative x is not the same as negative f of x. Okay, so not even, not odd. Therefore, this function is neither even nor odd. That's it. Of course, if you can graph the picture, you can also tell. You can also tell, right? You can also tell this is even or odd by the picture. But usually this is a kind of my preferred way to do it, right? Just go by definition, really just go by definition. That's even odd function. Okay, we have been addressing these issues because this semester, whether we're doing trigonometry or we're doing pre-calculus covering trigonometry or other areas, we will all need to know these concepts. We all need to know this concept. All right, summarize. Even function, definition, and the graphic, the picture, and the feature on the graph, and odd function and the feature on the graph, right? So when we understand both, and we could identify whether a function is even or odd. Anyway, thank you for watching. Until next time.